Good evening to all the participants and a hearty welcome to your 5-day International Faculty Development Program on applications of mathematics in various fields with innovative approaches. The aim of this FDP is to bring some sort of awareness on latest developments in differential equations, linear algebra, number theory, graph theory, and functional analysis and their applications. Today is a special day for the mathematics community, which is the 103rd birth anniversary of Sri Komaravolu Chandrasekharan Garu, who is a great mathematician and emeritus professor from the soil of Bapatla. He worked in the fields of analytic number theory and summability. He rendered his services to International Mathematics Union at various capacities as a member, secretary, and president between 1960 and 1980. He was the founding faculty member of School of Mathematics, TIFR, Bombay. I now request our senior faculty member, Sri N. Karunakar Garu, to compare the program.
A very warm and healthy good morning to our respected principal, Dr. Nazir Sheikh Garu, Bapatla Engineering College of Bapatla, Dr. K. Lacharli Garu, Head Department of Mathematics, and my dear colleagues and participants. I would like to welcome you on the occasion of 103rd birthday celebrations of a great mathematician, Dr. Komaravolu Chandrasekharan Garu, from the soil of Bapatla. He did remarkable research in the field of mathematics and contributed a lot with innovative ideas in summability theory and number theory. On this auspicious occasion, to pay our homage to him, the Department of Mathematics is conducting a 5-day international faculty development program on applications of mathematics in various fields with innovative approaches through virtual mode. This program scheduled every day from 4 p.m. to 6 p.m. from 21st November to 25th November. Approximately 975 faculty members from various educational institutions across the country have registered for this FDP. The objects of this FDP are to foster a culture of life learning process among faculty members by motivating them to remain up to date on cutting edge research, educational needs, and a creative approach to teach mathematics. To promote interdisciplinary methods among faculty members, showing how mathematical ideas may be used in variety of academic fields and real-world situations. To serve as cornerstone of the continuous improvement and enriching the knowledge in faculty members with innovative teaching methodologies. On the first day, 21st, that is today, Dr. N. Sudhakar Garu, Professor, Department of Computer Science Engineering, Bapatla Engineering College, Bapatla, will deliver a talk on machine learning models. On the second day, 22nd November, Dr. KVV Varprasad Garu, Associate Professor, Department of Mathematics, Guru Ghasidas Viswavidyalaya, a Central University, Bilasapur, will deliver a talk on problem of discontinuity at a fixed point. On the third day, 23rd November, Dr. C. Pavan Kumar Garu, Faculty of Mathematics, Apex Max Excel Center, North Carolina, USA, will deliver a talk on applications of linear algebra in machine learning. On the same day, Dr. N. Panikumar Garu, Professor and Head, Department of Mathematics, Vijnan Institute of Science and Technology, Hyderabad, will deliver a talk on Introduction to Mathematical Modeling in Ecology and Epidemiology. On the fourth day, 24th November, Dr. P. Anuradha Kameswari Garu, Professor, Department of Mathematics, Andhra University, Visakhapatnam, will deliver a talk on solving minimal solution of a Pell's equation using lattice reduction. On the fifth day, 25th November, Dr. J. Bhaskar Bapuji Garu, Professor, Department of Mathematics, Anna University, Chennai, will deliver a talk on topological analysis of molecular graphs and drug design. On the same day, Dr. D. Pratap, Associate Professor, Department of Mathematics, CMR Institute of Technology, Bangalore, will deliver a talk on graph labeling of the type magic, bimagic, and anti-magic. Now I request one of our staff organizers, Ms. I. Rajeswari, to give a life sketch of Dr. Komarolu Chandrasekharan Garu.
Good evening to everybody. Now, I submitted a brief biodata of Dr. Komarolu Chandrasekharan Garu. Komarolu Chandrasekharan Garu was born on 21st November 1920 in Machilipatnam in Andhra Pradesh. He had his high school education at Bapatla. Later, he obtained his MA in mathematics from the Presidency College, Chennai. He was a research scholar in the Department of Mathematics, University of Madras during 1942 to 43. He worked as a part-time lecturer at Presidency College and obtained his PhD during 1943 to 46. He pursued his PhD from University of Madras Sri Srinivasa Ramanujan in Cambridge. Afterwards, Chandrasekharan went to the Institute of Advanced Study, Princeton, USA. In 1949, he was invited by Homi Bhabha to join the School of Mathematics of the Tata Institute of Fundamental Research, which is known as TIFR. He molded the upcoming School of Mathematics of TIFR into a center of excellence, which is respected all over the world. Now it has become an extraordinarily gifted organization. He initiated a very successful program of recruitment and training of research scholars at TIFR. The program continues till today on the same lines that he set down. He put to excellent use his contacts with the leading mathematicians of the world and arranged their lectures. The lecture notes prepared out of these lectures, which is published by TIFR, enjoy a great reputation in the world mathematical community even today. During 1945 to 61, he was a member of the Executive Committee of the International Mathematical Union. He served as the Secretary of IMU during 1961 to 66 and as President during the years 1971 to 74. His initiatives over a long period of 24 years on this committee were numerous and valued greatly. He extended his services as the Vice President of the International Council of Scientific Unions during 1963 to 66 and as its Secretary General during 1966 to 70. He was a member of the Scientific Advisory Committee to the Cabinet Government of India during 1961 to 66. He was awarded the Padma Shri in 1959, Shanti Swarup Bhatnagar Award in 1963, and the Ramanujan Medal in 1966. He was responsible for International Mathematical Union sponsoring the International Mathematical Colloquium held every 4 years at the Tata Institute starting from 1956. In 1957, on his initiative, TIFR published the Notebooks of Srinivasa Ramanujan. In the 50s, Chandrasekharan held the editorship of Journal of the Indian Mathematical Society. Several great papers of revered research scholars were published in this journal under his able editorship. In 1965, he left TIFR and moved to Zurich, the largest city in Switzerland. He worked in the fields of number theory and summability. His mathematical achievements in the areas of analytic number theory, classical Fourier transforms, elliptic functions, topological groups, arithmetical functions, typical means, etc. are a landmark in the field of mathematical research. In the year 2012, he became a fellow of the American Mathematical Society. This great mathematician and a worthy son of Bapatla, Professor Komarolu Chandrasekharan, passed away on 13th April 2017 in Zurich at the age of 96. In this connection, I humbly inform to you all that our research team paid our homage to this eminent mathematician by acknowledging him in our research papers and also FDP on his 103rd birth anniversary celebrations. Finally, on behalf of all of us, I pay my homage to that departed soul. Thank you, one and all.
Thank you, Rajeshwari, for your informative life sketch of Dr. Komarolu Chandrasekharan Garu. Now it is Now, I take it as a privilege to give the department profile. The department was established in the year 1981, in which the college was started. The department, which was originally intended to cater the needs of engineering, offered MSc course with an intake of 40 students in 1989. The department was recognized as a research center by Acharya Nagaj University from the academic year 2003-2004. The department got name and fame under the leadership of our former head of the department, Dr. Nagala Prabhakar Rao Garu. So far, the department produced 3 PhDs and 13 MPhils. The department was recognized as one of the potential departments in 2002 by the National Board of Higher Mathematics. And as a part of it, the department has received quality books in mathematics, which are very useful for students and staff for their higher learning in their research. The department is now enriched with 6 PhDs, faculty members from different universities. The college library has a collection of 1,323 titles, 4,618 volumes. Out of 32 MSc Max passed out batches, 12 students achieved university first rank, 4 students obtained university second rank. 2 students received Pratibha Awards. For the last 1 decade, 200 research papers were published in national and international journals. The major contribution has been given by Dr. K.V. Nacharlu sir, approximately 140 research articles, and Dr. N. Rafi sir, approximately 44 research articles. Faculty members in our department attended more than 150 faculty development programs, workshops, conferences, seminars. Notable achievements are accomplished by the faculty members. In particular, Dr. K.V. Nacharlu created 3 unique world records in the field of mathematical research and honored with many awards and rewards. He authored 5 books and 10 chapters in various international publications. Faculty members in the Department of Mathematics completed 12 online courses for enriching their knowledge. Now I request our head of the department, Dr. K.V. Nacharlu Garu, to address the participants on this occasion.
Good evening to all. On behalf of Maths Department, I humbly welcome you to this International Faculty Development Program. It gives me immense pleasure to take this opportunity to say a few words as Head of the Department of Mathematics, Bapatla Engineering College, Bapatla, on this memorable occasion of the birth anniversary of Professor Komaruvolu Chandrasekharan Garu, who is applauded as one of the great mathematicians in the world. He hails from the soil of Bapatla. Bapatla is a prestigious center for its cultural, literary, spiritual, dramatic, and educational heritage. Professor Chandrasekharan Garu brought name and fame to Bapatla in the field of mathematics. His unforgettable research and most valuable contributions to the field of mathematics are a pride to Bapatla. It is my first and foremost duty to show my special gratitude to our magnanimous management for their constant encouragement for conducting various useful programs. We are all grateful to our dynamic principal, Dr. Sheikh Nazir Garu, for his unforgettable guidance and valuable support in 24/7. I am very happy to inform you that our college got NAC A+ under his able leadership. The main purpose of conducting this international FDP is to focus on innovative teaching methodologies with the best practices. It will help to our teaching community to explore new ways of engaging students, fostering critical thinking, and adapting to evolve educational needs. Moreover, FDPs encourage and support faculty members in their research endeavors. FDPs contribute to maintain and improve the overall quality of education by providing tools and insights for faculty members into quality assurance process. In addition to it, participation in FDPs can boost motivation and confidence among faculty members. It also helps us for professional development and improvement of the educational system, which are highly essential to the society. Thus, faculty development programs play a vital and important role in enhancing the capabilities of the faculty members, promoting innovative approaches in teaching, and ultimately contributing to enhance the overall quality of education. So this program will be definitely a fruitful one with your valuable participation and collaborative cooperation. The resource person for today's session is Professor Nagala Sudhakar Garu. He rendered his valuable services for 36 years in Bapatla Engineering College. All through his career, Professor N. Sudhakar Garu inspired thousands of students and also faculty members and won fame as a best teacher. His services as a head, professor, principal, and various academic key posts of Bapatla Engineering College were highly acclaimed. We are all inspired by him in multifarious aspects. Simply, I can say that he is the best role model to all of us. I conclude my speech with recalling a great and inspiring person, former HOD Dr. Nagala Prabhakar Rao Garu, who molded our maths department very strong with his worthful efforts and systematic executions. Finally, our strength is our faculty members. All the best. Thank you, one and all.
Thank you, sir, for your motivating by the telling the importance of the faculty development program. Now, I humbly request our beloved principal, Dr. Sheikh Nazir Garu, to give his valuable message on this memorable occasion.
Today's resource person, respected Dr. N. Sudhakar sir, Professor, Department of CSE, Bapatla Engineering College. Respected Dr. KVL Acharya sir, HOD, Department of Mathematics and convener of the FDP. Dr. T. Srinivasa Rao sir, co-convener of the FDP. Dr. K. Manideep, Department of CSE for technical support. Mr. N. Karunakar Garu, staff coordinator of the FDP. All the respected faculty participants, a very good evening and a warm welcome to this international 5-day faculty development program on applications of mathematics in various fields with innovation approaches. This FDP is organizing on eve of 1/3 birth anniversary of celebrations of a great mathematician, Professor Komaravaram Chandrasekharan Garu. As per the data shared by the convener of the FDP, Dr. KVL and Acharya Garu, happy to know that participants are from in and around colleges, other states, and even other countries also. It's because of the meticulous content prepared by the convener and his team members, and the selection of eminent resource persons for delivering of the content coming 5 days. I congratulate to Department of Mathematics for conducting International 5-day Faculty Development Program. I'm sure and I'm confident the 5 days will be more interesting and informative topics will be covered by the eminent resource persons. With this, I thanks once again to the Department of Mathematics for giving me this opportunity. Thank you one and all.
Thank you very much, sir, for your inspiring speech. This is the time to know about today's resource person. Now, I request one of our staff organizer, Ms. K. Sunita, to present the profound profile of Dr. Nagala Sudhakar Garu.
Good evening, welcome you all to a 5-day International Faculty Development Program of Mathematics in various fields with innovative approaches. A privilege to introduce today's resource person, Dr. N. Sudhakar Garu. Dr. Nagala Sudhakar Garu is the senior most professor working in the Department of Computer Science and Engineering, Bapatla Engineering College, Bapatla. He did his BTech in Mechanical Engineering from Visvesvaraya Regional College of Engineering, presently NIT Nagpur. MTech in Computer Science from NIT Warangal and PhD in Computer Science and Engineering from Acharya Nagarjuna University, Guntur, for the thesis titled Perceptual Structural Similarity for Image Quality Assessment. He has published 21 research papers in various reputed international journals. 4 students obtained PhD under the guidance of Dr. Sudhakar Garu. Presently, Dr. Sudhakar Garu working in the areas of data structures, algorithms, and machine learning. Professor N. Sudhakar Garu is applauded by one and all with his best way of teaching for the last 3 decades. Moreover, his valuable services to the college in different positions as head and principal are marvelous. His contributions as a pillar in the development of our college are remarkable. His inspiring character, motivational behavior, teaching abilities, research capabilities, extraordinary communication skills are additional qualities in him apart from his goodness and vast experience in the field of education. Thank you.
Thank you, Sunita, for your nice introduction about Dr. N. Sudhakar Garu. I know that you are all eagerly waiting for the lecture on machine learning models. Hence, I hand over the session to Dr. N. Sudhakar Garu.
വാട്സാപ്പിൽ എനിക്ക് എന്തെങ്കിലും മെസ്സേജ് അയക്കും. വാട്സാപ്പിലല്ല, ഇൻസ്റ്റഗ്രാമിൽ. ഇത്രേ ഉള്ളൂ. സുഖാണോ? ഫുഡ് കഴിച്ചു. ഇതിനെപ്പറ്റി ഇത്രയും ചിന്തയുള്ള ഒരാൾ എല്ലാ ദിവസവും അയക്കും. അത് തമാശക്ക് പറഞ്ഞാലേ നമ്മളെ ആരായാലും ഫ്രണ്ട്സ് പോലും ഇല്ല, ആരുമില്ല നമ്മുടെ അടുത്ത്. അങ്ങനെ മക്കള് പോലും ഇല്ല.
Sir, some of you switch on their mics so that it is disturbing us also.
Good evening, one and all. I hope I am audible to all of you.
Yes, sir, it is audible, please.
I got the confirmation. Thank you. I am really privileged to be a part of this workshop, which had a national exposure. I just came to know that this workshop participants are all across India. I really feel privileged. Also, I am grateful. I'm elated by the good words spoken by all the people who are associated with the conduct of this workshop. Thank you, sir. Thank you, one and all. The coordinators, conveners, and the head of the Department of Mathematics, K.V.L. Acharya Garu, and the principal of our college, Dr. Sheikh Nazir Garu, who has a great leadership skills in motivating all the departments to do illustrious academic and curricular and co-curricular activities. So as a part of this workshop, I have been given a slot today, and I will be talking about machine learning models. I know you are all from one-way hardcore mathematics domain, but the kind of topic what I am going to talk about is also related to mathematics. It's purely related to mathematical modeling only. So without any much ado, I'll get into the topic. So I hope the screen is visible to you. Yeah. The topic what I am talking about is artificial neural networks. Of course, you might be surprised that today's topic title is machine learning model. So artificial neural networks is one of the machine learning models. So what are machine learning models? Machine learning models are the ones which learn from data. Or in other words, you can say that you have a lot of data, you would like to find out a function that maps the input variables to the output variables. So that should sound very familiar to you in the domain of mathematics. So we have a lot of independent variables, and then we have one dependent variable. And one dependent variable of any size. I don't mean variable means a scalar variable. It could be a vector also. So you have a lot of independent variables, and you have a dependent variable of different sizes. And now what machine learning does is it tries to find a function that maps the inputs to the dependent variable or the output. That is the whole idea of machine learning from the perspective of mathematics. Of course, I am slightly deviating from the conventional definitions because I want to make you feel at home rather than go into a very classic definitions of machine learning and all. So as far as this lecture is concerned, I'll focus on how to map the set of independent variables to the corresponding output variables or dependent variable. Now the model I have chosen, there are several models. Each model has a different learning capability. Each model has a different methodology for this function approximation of mapping the inputs to the independent variable. So one of the models is artificial neural network. I have chosen artificial neural network because of its power, the capability of artificial learning in learning a broad range of functions being one aspect, being able to learn the broad range of functions. And the second aspect is it's very close, the structure of the model is very close to the human brain. So these are the two reasons why I have chosen the topic artificial neural network. And of course, artificial neural network is the fundamental model based on which deep learnings and other areas of learning are also based on. This is the foundation. So as the slide says, artificial neural networks are machine learning models inspired by the functioning of human brain. So the structure of your artificial neural network is very close to the structure of how neurons work in the human brain. And of course, the applicability of ANNs, where are they? What are they meant for? They are meant for solving regression and classification problems. Of course, you all should be aware that regression is a mathematical problem where you try to find out a mapping function. And then a classification problem, trying to find out what kind of data is it, which class does the given data belong to. And the power of ANN, I said, I have chosen ANN model because of its power, the broad range of functions it can approximate for the given data, where it will try to relate the independent variables and the dependent variable. So it's capable of finding out very complex decision boundaries. It's a different word what I'm using, but otherwise decision boundary is nothing but a function. Maybe this diagram should illustrate the kind of discussion what I have made so far. Let's suppose that we have two sets of data points that are given to us, which are plotted on the Cartesian plane. Each point is defined by two feature values. Of course, in the domain of mathematics, we say x coordinate and the y coordinate. But let's try to switch over to the vocabulary of machine learning. We say that each point is defined by two features. Maybe instead of being very abstract on the Cartesian plane, let me say that we have a set of students whose height and weight, or as patients whose height and weight have been recorded. So all these patients' height and weight have been recorded, and they have been plotted on the Cartesian plane. The result is these points. But I have not only shown the points, but I have shown two classes of points. One class of points where, let's suppose that on x-axis we have the height and on the y-axis we have the weight. So we have lanky people where the height is more and the weight is less. Such kind of people. Lean and tall people. Whereas this talks of short and weighty people. Short and rather obese people. So we see that lean and tall, short and weight. So these are the two classes of points what we have. Can you find out the decision boundary? So that if I have the equation of this line is being called as the decision boundary. So that if I have the line of separation, the decision boundary, the equation of this line, however you put it, then if a new point comes, I'll be able to find out if that point is above the decision boundary. I'll say that this patient is obese, and otherwise I'll say lean and tall. So this is the kind of learning what artificial neural network is capable of doing. But of course, this is only a very simple idea about the artificial neural network. Let's look at the second diagram. What is the difference between the first diagram and the second diagram? In the second diagram, we find that these data points, these patients, are not linearly separable. Whereas in the first case, the data points are linearly separable. Whereas in the second case, they are non-linearly separable. And in that case, the artificial neural network will be able to learn a non-linear decision boundary. So that's the next step where you can say that the artificial neural network can enhance its capability of data points are there. Now let's look at this third diagram where you have three classes of points, and we find that we have a very complex decision boundary here. It's a very complex decision boundary. And artificial neural network will be able to find out such complex decision boundaries in multi-label classification. So the ultimate idea is we have been given data. The data may consist of 2 classes, 3 classes, 4 classes, or n classes. And the decision boundaries can be as complex as possible on this earth. And the artificial neural network tries to learn from the data and converges to a meaningful decision boundary where it tries to correctly classify all the given data points. Maybe this is a breakpoint where I will try to get the feedback from at least a couple of the participants. Will they be able to, from a couple of participants, is the problem statement clear so far? You can unmute your mic and share your questions, or yeah, I find one of them have raised their hands. Dr. Sampath Kumar, Sachin Trivedi, Sampath Kumar or Sachin Trivedi. These are the two people who have raised their hands. So if you have something, you can unmute your mic and share with me. Okay, that's fine. Anybody else who will just give me a feedback of whether I am with you?
Hello, sir. Good evening, sir. Hello.
No.
Hello.
Maybe can I ask randomly somebody?
Sir.
Balaji Prakash. Yeah, CH Ram Gopal. Can you unmute your mic and share your feedback? You have raised your hand. Is there any problem with the mic? Okay. Can you at least type in the chat box?
Dear participants, if you have any queries, please put a message in chat box.
Good evening, sir. Sir, actually, chat is disabled for us. Is not.
No, I expect at least one of you to speak, so that we know that you are there and you are listening, and I'm able to convey to you. I believe so. Oh, enable later. When is it later? I think they can. Hello, mic is there. They can unmute and speak. Dr. Satish, can you unmute your mic, Dr. Satish? Are you able to unmute your mic? Let's know about the settings.
Yes, sir. We are able to hear you.
Yes, sir.
Yes, sir.
Sir, yes, sir. We can able to hear it very clearly, sir. You can proceed, sir. We can understand everything. It's very useful and very clear, sir. But we cannot write anything in the chat box, sir.
Chat is disabled, sir.
Okay.
It's okay. Proceed, sir, please.
I'll continue then. We will see if settings are not given. I am very much sure that you have the capability of unmuting your mic and saying something. But anyhow, some of you have raised your hands. So now if you get back, you find that I have titled this as function approximation. So we all should agree that this is nothing but function approximation. Now let's take a real world problem where we have two types of iris flowers. In fact, there are three types of iris flowers. Let's consider, for the sake of introduction of artificial neural networks, two types of iris flowers. I'll tell you why we have started with two, and then how we will move on to three. So these two types of flowers, iris setosa and iris versicolor. So you see their photographs. But however, every iris setosa flower and every iris versicolor flower are distinguishable. Definitely they are distinguishable. They're separable. What is the criteria for separating these two flowers? The criteria is every flower has sepals and petals. So looking at the sepal length and the petal length, you can easily differentiate the two kinds of flowers. So let's look at this. Now I have converted the real world problem into a mathematical statement. So you see that you have a sepal length 5.1 centimeters, petal length is 1.4 centimeters, and then the class of the flower is iris setosa. What you see in the previous slide, it is iris setosa. And we have one more flower with slight variations of sepal length and petal length, but still it purports to be iris setosa only. 4.9 and 1.4 centimeters each, sepal length and petal length. SL stands for sepal length, then PL stands for petal length. And similarly, let's look at the other kind of flower. If you look at the other kind of flower, the sepal length is 7 and the petal length is 4.7. This is iris versicolor, the second class of flower. 6.4 and 4.5. This is another kind of versicolor flower only. So you see that though they belong to the same class, it's not necessary that all of them should have the same sepal length and petal length. The sepal lengths are in a range. The petal lengths are in a range. If you observe at this small amount of data, of course, when the amount of data is very large, it becomes very difficult for tractability. But however, I have given you only 5 plus 5, 10 examples. So in these 10 examples, we see that the sepal length of iris setosa is oscillating around 4.5 or 4.6 to 5. The petal length is very in the range of 1.3 to 1.5. Whereas when it comes to iris versicolor, we see that the sepal length varies from maybe 5.5 to around 7, and the petal length is quite distinguishable, and it's around 4 to 5. The range is from 4 to 5. So by looking at these 10 examples and 2 variables, maybe you feel that you can judge by human sight. But we are not looking at such a kind of example. This is only a toy example where will they be able to chat and will they be able to speak? What is it? Will the participants? Were they permitted to that? Okay. So you are all permitted. Once again, I got confirmed from our technical team. You are all permitted to chat and also to speak. So we will be very happy if you can share your opinions in between the lecture. So maybe for these 10 examples, you will be able to easily find out classification by human judgment by looking at the data. But imagine if you have not 2 parameters, sepal length and petal length, and if you have 10 parameters that define each class of flowers. And moreover, let's not assume that there are only 2 classes of flowers. Instead, there are around 10 classes of flowers. I'll give you a real-time example where handwritten digits are there. 0, 1, 2, 3, 4, 5, 6, 7. You have 10 classes there. You want to recognize which digit is it. You want to make your artificial neural network, given a handwritten digit, image of a handwritten digit, it should be able to find out whether it is 0 or 1 or 2 or 3. There are 10 classes. And similarly, if I give an image of 28 by 28, then you see that you have around 764 values. So 764 values map to 10 classes. Whereas here, you are talking about only 2 values mapped to a single 2 classes. And moreover, by the side of the class, I have put label. Because when you are trying to learn with a mathematical model, you cannot be able to output words like iris setosa and iris versicolor. In fact, iris setosa is encoded as 1. It is represented by a value of 1. And the second kind of flower, iris versicolor, is encoded numerically as 0. Or you can do the other way around. Iris setosa as 0, iris setosa as versicolor as 1. So you realize that ultimately we have a real-time data set, organization of features and the labels, features and the labels, in the domain of mathematics, dependent variables and independent variables. It's called as a data set. So we have a data set here. Now the whole idea is we want to have a model which learns by looking at this data. So I have lot of data available. So I'll give this data to the model. Presently, we are talking about artificial neural network. So we'll give the data as input one after another. So we'll say that the input is 5.1 and 1.4 sepal length and petal length. And train yourself so that your output should be 1. 4.9 and 1.4. Train yourself so that the output should be 1. 6.4 and 4.5. Train your network so that the output should be 0. So we see that this is called a supervised learning. It's called as supervised learning because we're trying to give the features, independent variables, and we are trying to give the independent variable at the end, so that it will try to learn some mechanism internally of mapping these features to the labeling, mapping the independent variables to the dependent variables. So that is the whole idea of training a model. So I have introduced another phrase here, training a model with a data set. We have the known data set where we have features and labels, and these features and labels are input to the model. The model takes the features, tries to learn, has some internal parameters. It will modify its internal parameters to learn the values of these parameters. So that finally the output will be the desired label. Maybe you can ask me a question, what is the use of this? When I train the network on a known data, tomorrow, probably, if I get a new set of values of sepal length and petal length, this model will be capable of telling me immediately. I need not try to make my own judgment of looking at the data set. And especially, I told you, human judgment is very complex when the number of features exponentially grow and the number of classes what we have in the labels also grow. So what we try to do is, tomorrow when I get a new sample of a flower, I do not know whether it is iris sedosa or iris versicolor, but I got two values of sepal length and petal length. And this model has been already trained on known data. It has undergone supervised learning. We have shown the data to it. So now I give the unknown sample, and it will output, probably it will predict what is the correct class of this given sample. So once again, I treat this as breakpoint, and I would like to interact with the attendees. So can you just give me some kind of feedback where I'm trying to make sense to you and you are able to understand what I'm trying to explain?
Yes, sir, we are getting it.
Yeah, Pankaj Patil. Can you unmute your mic and speak?
Yes, sir.
Yes.
Yes, sir. We are getting the machine learning algorithms can be made by using a model. Yes, sir. Am I audible to you? Hello? Hello, sir. Am I audible to you? Hello? Hello?
Are guests allowed to speak?
Hello, sir. Am I audible to you? I have unmuted from my side.
If you have any questions or if you have any feedback, can I see the chat box? Q&A. Okay. Can you give your feedback? Is there anything wrong? Nobody is speaking. Yeah, you can unmute and see. Let us just check. Are you an attendee or a presenter?
I am an attendee, sir. Myself, Dr. Ram Gopal.
Is there any problem?
Sir, am I audible?
Does not have an email account. We can. Okay. None of them are unmuting.
Hello, sir.
No, let us know at least if there is any problem. We should know. That's the reason. This workshop should go for 5 days.
Am I audible to you?
So we want to know whether you are able to communicate or not. Yeah, Ravi Lakshmi.
Yeah,
Yeah, I could see.
yeah, that's what.
But can you be able to, Wasim Akram, can you unmute your mic?
Yes,
Are you able to
yes, sir.
unmute your
Yes,
mic? That we want to know. Yeah,
yes, sir.
you have
We can
unmuted
unmute.
your mic if I'm right.
Yes, sir.
But you can
We
go
are
ahead.
getting. We are having
problem.
the
If they do not have a team account, they will not be able to speak. They can speak. Oh, Wasim, can you unmute and say something so that we have the confidence that the communication is two-way?
Yes, sir. Yes, sir. I can unmute myself, and we are getting what we are following your slides, sir. As we are having approximation to the functions, and just we have seen the example. These were the 10 examples, 10 rows of the data set for particular and that.
Oh, we are extremely delighted. So we were in a doubt whether we are reaching you or not. And are you comfortable with that? Wasim, thanks a lot. Maybe can somebody else, maybe Wasim? Nice.
Hello, sir. Myself, Dr. Ram Gopal.
Yeah, Dr. Ram Gopal, one of you, Ravi
Yes,
Lakshmi.
sir. Yeah, myself,
Yeah,
Dr. Ram Gopal. Actually, the problem statement is very clear, and the topic is also interesting, and we are waiting for further session
yeah,
also.
sir.
Thank you very much.
Yeah. We'll go ahead, sir. Ravi Lakshmi, thank you for you also. And we have understood, we got the feedback. We were in doubt whether.
Thank you very much, sir.
Yes. Okay. We'll go ahead. We got confidence now. We were slightly skeptical. I'm getting back to my presentation. Fine. That's very nice. We got good feedback. So we got exactly, Wasim was telling, 10 rows were there, 10 samples were there, 10 data points were there. You can use this vocabulary prevalently. Authors use different kinds of words and vocabulary. So all of them mean one and the same thing. We have a data set in which 10 samples, 10 rows are there, and we have labels and supplemental length and pattern. Now, what is the artificial neural network model? So let me take one pointer. So this is basically called as artificial neural network. This is called as artificial neural network. Now let me explain you the structure of this artificial neural network so that we'll see what kind of functioning it does or what is the working basically.
Most of you are mathematicians, so it should seem to you very familiarly as a graph. But it's not a graph. It's not a graph. But you should feel comfortable, at least by keeping in the back of your mind, that we have nodes and connected edges. But in the context of machine learning, artificial neural network, we call these things as neurons. 1, 2, 1, 2, 3, and 1. They're all neurons. And we see that the first two neurons have been put at one level, the next three neurons are kept in the next level, and the last neuron is kept at another level. This is the structure of your artificial neural network. So this artificial neural network consists of different layers. So these levels, what I said for your convenience, technically are called as hidden layers. The first layer is called as the input layer, and the last layer is called as the output, for quite obvious reasons. Because we are trying to do function approximation, we have input features, and that should be mapped to a. So the number of neurons in the input layer will be dependent on the number of features in our data set. For example, the features in our data set are 2 in nature, supple length, and petal length. So what we do is, to this layer, input layer, we will input in place of x1 5.1 and 1.4. Fine. And this will travel through the artificial neural network. Let us assume that it has been trained already. It is knowledgeable enough. It has gained the knowledge of classifying iris retosa and iris classical. I'll tell you how it will gain the knowledge. Suppose it has gained the knowledge, then we have given 5.1 and 1.4. So it will undergo through several stages of values being calculated, and finally you will get one output value. And what should be that output value? If it has learned from the data successfully, the output value is 1. Similarly, in place of 5.1 and 1.4, if I give it the values of 4.6 and 1.5, I should get a value of 1 second. And if I give the values of 5.5 and 4, I should be able to get a value of 0. The same artificial neural network, this time should give me a value of 0. Similarly, if I give an input value of 7 and 4.7, I should get a value of 0. Of course, I'm trying to make it as simple as possible. I just said that from this data, this artificial neural network learns. So there is no point in giving the same values because it has already seen the value. But just for the sake of understanding, I'm telling you, even if I give these values, it should be able to give the original labels. But the most interesting thing for us is, if I give a value of 7.2 and I give a value of 3.9, which is not there in the data set from which this artificial neural network has been trained. It is an altogether a foreign point. It's altogether a new sample, new feature vector. I call it a feature vector because it consists of two values, so I call it as a random. So I give a new feature vector, then it should be really interesting to know what should be the output of this learned, trained artificial neural network. Quite obviously, from the data, we expect that this artificial neural network, if it has learned properly from the previous training data, what we have given to it, it should most probably output a value of 0. Similarly, if I give a value of 4.2 and 1.2, which is not there in the seed data set, which is not there in the data set based on which the neural network has been trained, it should hopefully give a value of 1. So for 7.2 and 3.9, it should predict. The word is predict. It should be able to predict a value of 0. And for 4.2 and 1.2, hopefully it should be able to predict a value of 1. So that's what the artificial neural network is expected. So now let's see how does it work. Now every neuron, let me further explain the structure of this artificial neural network. We have two neurons in the input layer in this example, but there is no limit. This is determined by the number of features in the input. The hidden layer can have any number of neurons. For the sake of simple explanation, I have taken 3 neurons. So you see that the first neuron in the input layer is connected to the first neuron in the hidden layer along an edge which carries some weight. Similarly, the first neuron in the first layer is connected to the second neuron in the hidden layer, which is called as along an edge. Weight is W1, and the weight of this edge is W11. Similarly, we have an edge connecting the first neuron in the input layer to the third neuron in the hidden layer along an edge. Weight is W1. The label of this edge, the weight along this edge is W1. And then the second neuron in the input layer is also connected to the respective neurons in the hidden layer, and the weights are W21, W22, and W2. If there were to be a third neuron, once again it will be connected by 3 edges to the neurons in the hidden layer along different edges, and the weights will be W31, W32. Yes. And then, in addition to this, every neuron in the hidden layer will have an associated term called as a bias. So this bias is represented by B1. Similarly, the bias associated with these are all floating point values. These are all real numbers. So the bias associated with the second neuron is B. The bias associated with the third neuron is B. Now, what is the purpose of this connection? So the purpose of this is 5.1 is transferred along this edge whose weight is W11. So the input value x1 is multiplied with the W11. And similarly, the input value of x2 travels along the edge W21 and gets multiplied by W1. So we have the sum of two products, x1 into W11 plus x2 into W21, and this sum will reach this neuron, first neuron in the hidden layer. To this sum, we will add the third term, which is the bias of this neuron. This is called as the network sum for first neuron, neuron 1, which can be called as net 1. Similarly, you have a network sum for neuron 2, which is net 2 and net 3. Let me tell you what will be the equation for net 3. x1 into W13 plus x2 into W23 plus B3 should be the network sum for the third neuron. Similarly, the network sum for the second neuron quite obviously will be x1 into W12 plus x2 into W22 plus B1. So these are the three network sums that are computed by the neuron in the hidden layer. And now, to this sum, an activation function is applied. The function is applied. That's why I have drawn a sigmoid here. I have drawn the shape of a logistic function here because I'm choosing a sigmoid function, a logistic function, which definition is sigma of x is equal to 1 by 1 plus e power minus x. So it will apply an activation function quite close to the working of the human brain, where a lot of inputs will go to a neuron from different sensory units of human body. And then an activation is applied on these sensory inputs. As a result, you will have an output from our neurons, and that output will be converted into human actions and human emotions. The same kind of model is being used here. So now the output of first neuron will be called as H1. We name it as H1 because it is the output from the neuron 1 of the hidden layer. That's why it's called as H1. Similarly, we have H2. Similarly, we have H3. So finally, H1 is sigmoid of, because at the end we will apply an activation function. Sigmoid of this network sum. And I told you how to calculate the network sum. x1 into W11 plus x2 into W12 plus B1, to which you apply sigmoid function, you get H1. Similarly, H2. Similarly, H3. The same computational step happens between the hidden layer and the output layer once again. I have chosen, you might be asking me why you have chosen sigmoid function. Yes, there are different activations depending upon the statement of the problem, applicability of the problem, nature of the problem, and you can use different kinds of sigmoid functions, different kinds of activation functions. So I have taken the simplest function possible, that is the sigmoid function. And moreover, my output should be mapped to 0 and 1. Output should be mapped to 0 and 1. So it is only sigmoid function that will map any input to 0 and 1. So that's the reason why I have chosen a sigmoid function. But of course, one more question can be, okay, sigmoid function is needed in the output layer. Why should you limit yourself to sigmoid function in the hidden layer? Because it is open to apply any activation function. Yes, you are right. You can apply any activation function. Only if the output neuron or in the output layer, you will be constrained to look at what is the label you have to get and accordingly choose your activation. So once again, let's try to predict what will be the output based on the outputs of the hidden layer in the next stage. H1 into W11 plus H2 into W21 plus H3 to W31 plus this bias, okay, to which a sigmoid function is applied, and finally a return. So the question is, how do I get these weights and biases? These weights and biases are learned by the artificial neural network by looking at the known example, which is called a supervised learning. How does it learn the weights? We will take up in the next step. How does it learn the weights? That process of starting with random weights and being able to learn the correct weights so that from the training data set it will learn, start with some random weights and biases, it will slowly modify and choose these weights and biases till it will be able to correctly classify the known samples, then it will be ready for being able to classify the new unseen sample. That is the whole idea of it. How this training has to be done, how the training algorithm works, you will see in the next few slides. The main emphasis now is, the main emphasis now is on how the artificial neural network works. So we have assumed that it has learned, and we are trying to find out how does it work based on already the learning. But the biggest question is, how does it learn? So now this descriptive explanation what I made, let us try to convert it into a mathematical computation. Fine. So this is the big flow diagram. Here I wanted to have the data on one side and the network on the other side. I will go both of them at a time and then try to explain. Now I have separated the data. I have given you once again the same artificial neural network. Excuse me. Something that slightly cold. So this is the same blown-up diagram of what was shown in the previous slide. So I'll go on to the next slide. This explanation I have given already, that an artificial neural network consists of different layers of neurons. Maybe there could be one more question. You have shown one hidden layer. Can I have more hidden layers? Can I have more hidden layers? Yes. You can have as many number of, excuse me. You can have as many number of hidden layers as needed depending upon the complexity of learning. Here I have shown only one hidden layer. This is the hidden layer. I have shown one hidden layer. But you can have another hidden layer. And moreover, I have shown only few neurons in the hidden layer. Is there any limit? No, it's a design choice. After getting experience with working with machine learning models and artificial neural networks, you will be the best judge for the given data set. What should be the structure I should choose so that I will train my artificial neural network on the available data, and the neural network will then be capable of classifying the unknown samples, giving the output for the unknown samples. Similarly, the output layer here has one neuron. So why does this neuron artificial neural network has only one neuron? Because the label value what we want to have is a scalar. So because it is a scalar, it's good enough that I have one neuron in the output layer. Suppose I would like to have a vector in the output layer. My label is not a scalar value, but instead it is a vector consisting of 3 values or 4 values or 5 values. And then this output layer should have 1, 2, 3, 4, 5 neurons if the vector which has to be predicted, the label which has to be predicted, the output value which has to be predicted should have 5 values. So that way, all these are variable parameters, which are called as the hyperparameters of the model. Hyperparameters of the model are the parameters which will describe the structure of your art. So once again, I conclude the description of artificial neural network by saying that the input layer and the output layer, the number of neurons in these two layers, the layers are decided by are determined by the feature values and the length of the label. output one. The number of hidden layers, neurons in the hidden layers are a design choice. It's a design choice. So I'll go to the, so these slides are the ones what I have explained so far. This is a small animation of how a particular neuron in any layer takes the inputs and calculates the values. So I have a small animation here. Any neuron J computes the network sum as x1 multiplied by w1j, x2 multiplied by wj, plus xi multiplied by wij, plus xi plus 1 multiplied by wi plus j, and finally xp multiplied by wpj, plus dj. You see that you have plus. So all of them are summed up by the neuron j, any of the layers, in one of the hidden layers. I'm trying to get the right one. And to which a sigma is applied, that is sum is calculated, and then you apply an aggregation and you get your. So the same is being shown here in the form of an equation. Network sum for jth neuron from the layers, from the neurons in the previous layer. Is this? Okay. So this is the network sum in the sum notation. Sigma j is equal to 1 to d. K is equal to 1 to d. Means there are d features. There are d input values. X k multiplied by w k j. Because the neuron what we are addressing is jth neuron. And the jth neuron has a bias of d j. So finally, in the shorthand notation, we have sigma k is equal to 1 to d x k w k j plus w. Okay, these are some of the activation functions. Required activation function is 1 by 1 plus e power minus x. X is replaced by 1 at 1. Or it could be a hyperbolic tangent function, whose output will be in the range of minus 1 to plus 1. 1 minus e power minus 2 times network power divided by 1 plus e power minus 2 times network sum that has been calculated by the neuron, to which this tangent function. Similarly, you have a third popular activation function. You have many more activation functions. I have shown only 3. The third function is ReLU, which is called as rectified unit. So it crashes all the negative values to 0, as you can see from the definition of the function, max of 0 comma net j. So if net j is negative, the output of this activation function is 0. And otherwise, if it is positive, the same network sum without undergoing any transformation will be out. So that's rectified. I'm trying to show once again the way the network sum is calculated and the way this activation function is applied. I have shown the animation in one of the reports. The same thing happens in calculating H1, H2, and H2. H1, H2, and after H1 and H2, H3 are calculated. H1 will progress to the output layer neuron plus H2 multiplied by W1 plus H3 multiplied by W31 plus the bias curve to which the sigmoid function will be applied and the output will be 1 or 6 when you get the value. So now I am getting into slightly mathematical computation steps. H1, H2, H3, what I have shown in the previous slide. I'm trying to view the expressions for the computation of H1, H2, H3. But what we do is, we do not individually calculate H1, H2, H3 values. Instead, being from the domain of mathematics and linear algebra, you should be able to establish the correctness of this calculation. So the vector H1, H2, H3, that is output from the hidden layer, 3 values are there because 3 neutrons are there, is obtained by applying the sigmoid function to the product of feature vector x1, x2, multiplied with the weight matrix between the input layer and the hidden layer. The weight matrix between the input layer and the hidden layer is W11, W12, W13. the weight of the edge connecting 1, the weight of the edge connecting first neuron in the input layer to the second neuron in the input hidden layer, and the weight of the edge connecting the first neuron in the input layer to the third neuron in the hidden layer. Similarly, the second row of weight matrix will tell you the weight of the edge from the second neuron in the input layer to the first neuron in the hidden layer, second neuron in the input layer to the second neuron in the hidden layer, second neuron in the input layer to the third neuron in the hidden layer, which is a 2 by 3 matrix. And you finally realize that the size of the weight matrix, is 2 by 3, or in other words, 2 is the number of neurons in the input layer, 3 is the number of neurons in the hidden layer. So if you call P as 2 and Q as 3, you realize that the matrix size is P by Q. And you see that 1 by 2 multiplied by 2 by 3, that should give you 1 by 3, a vector, plus you have the bias vector. All the 3 neurons in the hidden layer have 3 weights, B1, B2, B3. So that vector is added to these vectors. Please remember, vector addition here means point-wise addition or element-wise addition. So if you have 2 vectors of 3 values, the first value in the first vector is added to the first value in the second vector to get the first value in the result vector. Similarly, the second value in the first vector is added to the second value in the second vector to get the second value in the third, and so on. So finally, you see that this is the kind of computation what you can easily do. Of course, this follows from linear algebra and matrix algebra. So you see that the input feature vector is multiplied with the weight matrix and the bias vector is added, sigmoid function is applied to get the output vector of the hidden layer. So you can state it very precisely in terms of this matrix. Similarly, what should be the output value of the neuron, the only neuron, if the output layer? Of course, this discussion is very specific to the example what I have shown you. And I think you should be able to generalize it to any kind of. So here we have the output of the hidden layer, which will act as the input to the output layer. So H1, H2, H3, 1 by 3. And we have the weight matrix. This time the weight matrix size is 3 by 1. The reason is quite obvious. It is 3 by 1 because you have 3 neurons in the hidden layer and 1 neuron in the output. So as a result, you have the first neuron in the hidden layer connected to the only neuron in the output layer. The second neuron in the hidden layer being connected to the only neuron in the output layer. The third neuron in the hidden layer being connected to the only neuron in the output layer. W11, W21, and W. So 1 by 3 multiplied by 3 by 1, you get 1 by 1. And of course, the output neuron, the neuron in the output layer has a bias whose size is also 1 by 1 because it is a single value. So 1 by 1 plus 1 by 1 should give you a single value, or it's a scalar value, or you can say that a vector of length 1, however you put it, a vector of length 1 or a scalar value. That should be your output. And because we have applied the sigmoid function, as I said, it should be a value between 0 and 1. And what we expect from a trained artificial neural network, I once again emphasize, we haven't seen training, we assume that it has been trained. We will see how to train it, but now we have seen how it calculates, how the sample is feed forwarded. This step is called as feed forwarding your sample, feed forwarding your data sample, couple length and petal length values, what we have seen in our data. So how this feed forward step is done is being seen now. Training will say the later. So you can hopefully get a value of 0 and 1. Maybe there could be a question, sir, what happens if I get a value of 0.8? Yes, there is every possibility that you very rarely get a value of 0 and 1 discrete values. The values can range from 0 to 1, but as close to 0 as possible and as close to 1 as possible if the neural network has been trained properly. And another interpretation of the values between 0 and 1 can be taken as the probability values of the given sample being of a particular process. be a particular class. Like I'll show you the data set once again. I'll go back. This is our data set. So the output, if it is 0.9, it can be thought of as probability of the given sample being iris setosa. Being iris setosa. So if it is 0.9, you can take it almost as iris setosa. This is another second possible interpretation. If I get a value of 0.2, then the probability of the given sample being iris setosa is 0.2. So what it means is the given sample is most likely to be iris versicolor rather than the iris setosa. Rather than iris setosa, because the probability value is very small, you say that it is most probably iris versicolor because the probability value is very less, it is 0.2. So you say that it is likely to be iris versicolor. So that way, now you should be confident enough to say that it need not be 0 and 1. Even if you have some value between 0 and 1, it can be interpreted as the probability of the given sample being iris setosa. If it is very large, it will be iris setosa. If it is very small, it will be iris versicolor. That is the whole idea. And quite reasonable. Yeah, I am expecting this question. So if it is 0.5, if it is 0.5, what I would like to say as a machine learning engineer is your network should not give a value of 0.5 if it has been well trained. So if it rarely gives a value of 0.5, then you say that it's probably difficult to judge. It could be iris setosa and iris versicolor, but that should not be a regular behavior of your language. That's what I would like to convey. There is every possibility of the value being 0.5, but please look at the value of 0.5 in this way. That though it has been trained very well, it is giving the value of 0.5, means that okay, it's very difficult to judge. It could be a setosa or versicolor. But if your artificial neural network has been giving for too many samples a value around 0.5, then there is something wrong with the training of your artificial. So maybe I'll consider this as the next big point, and I would like to listen to a few questions or feedback. That if you are comfortable, I'll proceed. Yes, sir. I'm having water, so I could not immediately respond to you. Uh, let me keep the data in front of you. What do you mean? What do you mean here? Very big data means. Are you meaning that instead of two input variables, do we have more input variables? Or do you mean that instead of two classes, maybe somebody? Yeah, you can. You can. I told you, if you input an image of size 28 by 28, you will have 28 times 28 pixel values. I think some of you should be familiar. Every image is defined by pixels along its width and along. No. Some of you, some of you, some of you should close the mic, please. Accidentally, you might have okay, now it's fine. May I know who is that asked the question? Can we extend into it? Okay, Dr. Ram Gopal, yes. Maybe anybody else other than Dr. Ram Gopal, can anybody interact, fire a few questions or share your feedback? Can you tell your name, sir? At any given time, I request only one of the participants to switch on your mic. If somebody else is talking, please switch off and then we'll give you turns. So whenever turn comes, okay, there are two people competing. We'll go with Shamshuddin. Okay, Shamshuddin, please. Yeah. Good evening. No, I told you in the initial stage, this is one sample, I have been given 2 hours of time. I'm trying to introduce you to machine learning. So I'm trying to just introduce you to how to learn from data. Learning from data can be done in several domains, in several ways, using several models. For example, I have been yeah, please. Yeah, Shamshuddin, is it clear? Can I move on to the next attendee? Okay, Dr. Narmada Devi. Good evening. Yeah, correctly. Yes. Okay, okay. Maybe we are not concerned. Okay. No, no. What we do is, I got your question. Suppose if there are, yeah, yeah, I got it. I got it. But I will try to answer your question from a slightly different perspective, from which you can deduce how will it be related to something. What we do in machine learning models is we try to, once again, I'll put the data in front of you. We try to convert these real world classes into some kind of labels. So the label what I have used here is 0 and 1 because I have two classes. Okay, probably that might have triggered the question from you. But let me give you another example where I have three classes. Iris setosa, iris versicolor, iris versicolor. I have shown 50 examples, but it could be few thousands. 1,000 iris setosas, iris versicolor, and 1,000 versicolors. 3,000 samples can be there, and 50,000. Normally, the data in the machine learning will be in the range of 50,000 to 1 lakh or more number of samples. So here, I have three samples. Now, according to the domain of machine learning, in the context of machine learning, in the context of artificial intelligence, these classes, which are real world names, because we cannot work with real world names in mathematical models, will be converted as vectors of 1, 0, 0, iris setosa, 0, 1, 0 is iris versicolor, and 0, 0, 1 is iris versicolor. This is the normal practice how we encode the class labels into encode. That's how we do it. So it's slightly different. You cannot bring fuzzy mapping into this, but this is how they are included. Probably your question might have been triggered by looking at 0 and 1, but the reality is I have vectors when the number of classes increase. Suppose I have 10 classes. So I have a vector size of 10 where the first class is defined by 1 in the first position, 0 in another position, all other 9 positions. The second class is encoded by 1 in the second position and zeros in the first position and remaining 8 positions. So you got my answer now? This is a slightly different context and a slightly different way of encoding, which may not have association with the fuzzy domain. Okay, that's good. That's nice. One of the participants have brought in another domain of. Sir Arvind Raju Garu, I think you have been trying to say something. Do you have anything to say, Arvind Raju? I have seen earlier Dr. Arvind Raju. Okay, I saw you muting your mic, so I thought you also have something to share. Anybody else? Good evening, Dr. Talpati. Yeah, please. Sure, sir. Sure. We'll do that at the end of the workshop. Don't worry, we'll share. Okay. Maybe I'll ask Dr. Arvind Raju, are you comfortable with the kind of lecture, the way the lecture is going on? Am I making sense? Is it getting to you? Dr. Narmada Devi, what's your opinion? Is it sounding familiar and are you able to understand? Okay. So, learning. Yeah. Yeah. What is the statement of the? Yeah. But otherwise, the discussion is making sense. The topic is sensible. You are able to understand. Yes, sir. Dr. Raghav Prasad, you want to say something? Yeah, I can hear you. Please share your opinion or questions. Very good. Hello, yeah, tell me. You said constant problem. What do you mean by constant problem? Hello? Tell me. Okay. What do you mean by number of constant values? Constant values. You said constant values. What do you mean by that? In which context it is that? I think the data is right now. You mean these values are 10? Okay, real life problem. Okay. Are you saying constant COLSK? Constraint problem. Okay. You are talking about constraint. Okay, constraint problem. You want to solve some kind of constraint problem. No. The domain what we are applying to is we have lot of data, we have independent variables and we have dependent variable, and we are trying to learn a function that will map the independent variables to dependent variables from the known data set, and then we want to predict the values of a dependent variable for unseen independent variable. That is the idea. So we're not talking about constraint optimization. Probably we're talking about operations research and simplex problems where you have a lot of constraints and optimization. No, we are not touching upon that. This is learning from data. Okay, that's nice, sir. That gave me some time. Yeah. It gave me some confidence that, okay. Okay. So that's fine. I think I have completed these equations. So now here, I'm trying to scale up the problem where we have three classes. Iris setosa, Iris versicolor, and Iris versicolor. And I have taken sepal length and petal length as the features of our input flowers, samples. I hope you remember these are the flowers. One is Iris setosa, another is Iris versicolor, Iris versicolor, real world data. But this real world data is converted into, a data that can be handled by mathematics. So how do you convert real world images into data? By characterizing some of those features. For example, here what I have chosen in the present statement of the problem is, we have chosen that sepals and petals will be there. Definitely there are three classes of flowers, plain sepal lengths and petal lengths will be different. So we try to characterize each by its sepal length and petal. Of course, if you want, you can add sepal width and petal width also, in which case you have four parameters with which you are characterizing your data. Fine. So now I have, but for simplicity of explanation, I have taken only sepal length. So I have three classes. So I converted the classes into encoding. So my data set is now applicable to be used in training and network. So now network becomes complex. I've taken four neurons. Okay. And then two inputs. So the hidden layer gives me H1, H2, H3, H4 as outputs. They are feed forwarded to the output layer. Now the output layer should give either 100 or 010 or 00. And I told you once again, these can be interpreted as a vector of probabilities. A vector of probabilities. 0.8, 0.8, rather 0.2, 0.2, and 0.4 or 0.6. The sum need not be 1. Because if you use acquired function, the sum of the probability need not be 1. But if you use some other function, then probably you can use functions where the output sum of the probability is equal to 1. So that way you have all possibilities. So if it is 1, then it is good. So you are using a activation function which results in the outputs of the neurons sum up to 1. So in that case, either you can take it as 001 or you can take it as 0 probability of setosa, 0 probability of versicolor, or 1 probability of versicolor. And 100 means 1 probability of setosa, 0 probability of versicolor, 0 probability of 010 means 0 probability of being setosa, 1 probability of 1 being versicolor, and 0 means the probability of being versicolor. So that's how you can always interpret the. So finally, we conclude that the number of neurons in the input layer is equal to the number of features of the data sample. The number of neurons in the output layer is equal to the number of classes what you are talking about. And the number of hidden layers and the neurons in the hidden layer is a design choice, which you will fine tune by training and checking, testing whether your network artificial network can be trained properly. So probably in this case, the equation will be H1, H2, H3, H4. We have 4 neurons, so it's a 1 by 4 vector. So 1 by 2 multiplied by a 2 by 4 matrix of weights between the input layer and the hidden layer. There's 4 biases of the hidden layer that should give the hidden layer. And O1, O2, O3 should give you, should be obtained as a sequoia function applied on the hidden layer outputs, H1, H2, H3, H4. And the weight matrix between the hidden layer and the output layer will be 4 by 3 because there are 4 neurons in the hidden layer, 3 neurons in the output layer. So the weight matrix will be 4 by 3. So 1 by 4 into 4 by 3 is 1 by 3 result. And you have 3 neurons in the output layer, so you have 3 biases. So 1 by 3 plus 1 by 3 should give you a 1 by 3 to which is required function is applied, which results in 1 by 3. Once again, I told you, it's all element wise operation. So you get an output of 1. That should hopefully be 1, 0, 0. Or it should be 0, 1, 0. Or it should be 0, 0. This is a standard practice of encoding the classes in artificial neural network and machine learning itself. See, I'll give you an example here. I have already trained one artificial and I have trained the artificial neural network on the data set, and the network has learned the weight matrix W1, P1, W2, P2. I'll give a small clarification of why the suffix superscript 1 and 2 are there. W1 and P1 are the weights and biases between the input layer and the hidden layer. Because you have weights between every 2 layers, we should not get confused which weight are you talking about. So W1 and V1, W superscript 1, V superscript 1 talks about weights and biases between the input layer and the hidden layer. W2 and V2, we have seen 4 by 3 and 1 by 3. They talk about the weights and biases. Okay, I'll keep this example and now let's see how you can get a feel of. Okay, I do some mathematical calculations and convince you that this network has been trained very well to classify. So I have done some mathematical calculations. We have some matrix algebra libraries with the help of which you can do these calculations very easily. Sir, one of you have turned on your mic, please. Okay, thank you. Now, Sachit Trivedi, please, can you switch off your mic? Your mic is getting turned on. I'll show you a just demonstration of calculation. Okay, so you can see the calculation part what we are doing. Let's look at the data. 5.1 and 1.4, it should belong to the class 100. And I am claiming that I have trained the neural network with lot of data, and the neural network has learned these weights. So let me try to show you the. So I have taken the input sample. The input sample is 5.1 and 1.4, as I have shown here. 5.1 and 1.4. And these are the weight matrices and biases. And let me define the weight matrix. I will use the same weight matrix 2, minus 9, 0.8, 1.3, minus 5, 8.2, minus 1.4, 0.26. In the same weight matrix. What I am claiming as the weight matrix learned by the artificial. Similarly, the biases 1.56 minus 17.7, 0.07. Let me give you a look. Yes, these are the biases of the hidden layer. what I claim to be learned by the artificial. And similarly, we have the weight matrix between the hidden layer and the output layer. Its size is 4 by 3 because there are 4 neurons in the hidden layer and 3 neurons in the output layer. So 7.8 minus 1.7 minus 2.6. This is the same matrix. And B2, the biases of the output layer, minus 2.2, 1, minus 0.5, so minus 2.2, 1, minus 5. So I have initialized the variables. The input sample I have taken is 5.1, 1.4. I have initialized W1. Hope this is visible. I am increasing the size also. So W1, I have defined the variable V1. I have defined the matrix W2. I have defined the vector V. And also I have defined a function segment x to calculate the program. So 1 by 1 plus e power minus x. So whatever x comes to it, it will return 1 by 1 plus e power. So now let me define this function also. Function is also defined expected. Most of you might be doing programming. You don't need to know programming. What I am doing is only mathematical calculation, kind of some library that is available. It's something like a calculator, nothing more. So you see that the void function is applied to the matrix product. This at the rate symbol corresponds to matrix product. X multiplied by W1, 1 by 2 multiplied by 2 by 4, 1 by 4. Plus B1 is 1 by 4. So 1 by 4 plus 1 by 4. The result is 1 by 4, to which I am applying segment function. So I got the value of each. Please watch this minus point, 10 power minus 1. Don't get carried away by looking at 9 multiplied by 10 power minus. And once I got the hidden layer output values, that is multiplied by the weight matrix between the hidden layer and output layer, that is W2. Once again, I will show you the neural network diagram. Yeah, this neural network diagram. These, I'll take a pointer and show you. So these are the 4 values what we got. Yeah, these are the 4 values. How did I get these 4 values? These 4 values are obtained by taking the 1 by 2 and by taking matrix of 1 by 4 and by adding these 1 by 4 biases, 4 biases are there. I got the values of each one. Then H1, H2, H3, H4 is feed forwarded and 1 by 4 vector multiplied with 4 by 3 matrix of reads plus these 3 biases are added and then you apply the segment function. You should be able to get the fine. I will switch over to the calculator. So I calculated the value. So you see that 0.98, 0.00, 0.0. To be able to understand this value, what I do is I round up this value without any loss of accuracy. So I got 100. So look at this, what I am supposed to get according to my data set. I should get 100. And I can say that this network has been trained well for input values of 5.1 and 1.4. It has given me a vector of 100. So let me test it with the last value, 6.5 and 5.8. I should get the value of 0.1. I'm not audible? Am I audible, sir, now? Okay, now let's take 6.5 and 5.8, the last value. So I'll go back, 6.5 and 5.8. What is it?
Yes, sir. Yes, sir. You are muted.
I'm audible, sir? Oh, no. Yeah. Sir, I am audible now? Yeah. I think, but I think by mistake the cursor, this pointer has pressed the mic. So maybe let me know. Was I audible when I was explaining the first round of calculation? Was I audible when I explained the first round of calculation? Okay. Now what I am trying to do is I am taking one this last one to give you confidence that whether it is capable of classifying all the three kinds of samples, 6.5 and 5.8. So what I have done is just I changed the input value of x, and then I will run through the same calculations. I have changed the value of x, I wanted to convince you. So let's say 6.1 and 5.5. I am not changing the values of W1, W2, W1 and W2. So my actual calculation will start here. I have to calculate the new value of H, the new value of O. Okay. And let me round up so that you get a better understanding. And you see that it has given you the output of 0.01. So, and that is supposed to the value what I have to get 0.01. Let me take this sample of 6.9 and 4.9, for which I should get an output value of 0.1. So let me go back. I will change 6.9 and 4.9. Okay. So let me change the value of x by running this cell. Let me check whether the value has been changed or not. Yes, 6.9, 4.9. I don't need to once again look at the weights and biases, they are fixed. Now let me feed forward this step. This step is called as feed forward. So I calculated the new value of h for this sample and calculated the value of O for this sample, and I have rounded up so that you can get an idea. Can you find that it is 0.1? So now are you convinced that the network has learned the weights and biases according to the wave function so that it can classify these three kinds of samples? Shall I take this as another breakpoint and look for your feedback? Yes, sir. I take this as another breakpoint, and because that completes the explanation of artificial neural networks, how it functions, how it learns the weights. Of course, I haven't told you about how it learns the weights, but we have assumed that it has learned the weights because I have run a program and trained the neural network and obtained the weights and biases. So I have taken those weights and biases and I have put them in front of you and then shown you the calculation so that you can get some hints about yes, this neural network has learned weights and biases for the current classification. Yes, sir. Yes, sir. One of you can share your feedback on the discussion we made so far. And this last leg of discussion, we had a meaningful understanding of artificial with a real-time example. Dr. Narmada Devi, you are there? Oh, yeah, please. Wasim Akram, please. Yeah. Okay. No. Artificial neural network is a supervised learning. Is a supervised learning. If you want to do unsupervised learning, you have to choose a different one. So maybe I haven't told you all these things because the time is short. Machine learning models are of two types: supervised learning models and unsupervised learning. In supervised learning models, the model looks at the labels and features, trains itself, and tries to predict for an unseen sample, the label for an unseen sample. In unsupervised learning, you don't try to give labels. You will train your model with unsupervised data, means only features will be there, labels will not be there. That's a different kind of artificial neural networks is a supervised learning. So it does not work for unsupervised. For unsupervised, you have different things. This is just one model in supervised. Supervised learning, once again, there are hundreds of models. This is the most popular model. Artificial neural network is a very popular architecture based on which you have somebody inside the convolutional neural network, natural language processing model, so ChatGPT and all. They're all supervised learning. Is any more? Yeah, please. Yeah, please.
Yes, sir. I just wanted to share the feedback that first, firstly, I was with the PhD for years. So I can live from computer science.
Very good.
And this is yes, one of the most important topic in neural networks. It was given in syllabus.
Very good.
I joined. Yes, I had joined this session for just information about the subject and the examples you have given was completely helpful. Yes.
Okay. Thank you, sir. Thank you, Abhishek. Thanks for your time.
Sir, can we suggest any book materials regarding this particular?
Okay. I'll give you. I'll show you the question. This is what goes book, artificial neural networks with tensor tools. And this is a very popular book, Sebastian Brunska. You can see Sebastian Brunska's YouTube lectures also. Introduction to artificial neural networks and deep learning. And if you want to have some programming kind of experience, this is the third book, Deep Learning with Python. This is from Annie's Publishers by Francois Scholen. These are the three books I use. One is from A Press, and one is from Sebastian Brunska, and another is from Scholen, Ram. Actually, I would have told you the mathematics of training also, but unfortunately, it's only a 2 hour workshop. And to this day, we first day we already lost half an hour. So that's the reason why I could not tell you how it is trained, how the artificial neural network will be able to learn this. But I thought I will give you an introduction that this is possible. Yeah, please, Abhishek. Oh, okay. Now am I audible, Abhishek? Okay. So I think Narmada Devi, Dr. Narmada Devi, these are the books. Did I answer your question? Oh. So I wish actually I would have taught you the mathematics of training, but this week, our lecture session, I could not do that. But I think you will get motivated and look at the mathematics of how an artificial neural network can be trained. This is purely an application of linear algebra and calculus. Which college do you belong to? Oh, okay. Okay, good. Sure, sure. I'll be more than happy to give my services. Any institution. Because maybe at this age, my only job is to teach and learn. Maybe I'll be delighted. Thank you, Dr. Nakana. I'll give you a complete mathematical view. In fact, let me just give you a. Yes, exactly. I'll just I'll just show you what kind of things I should have had the time been there, what kind of things I should have taught you. I'm just running through the slides. The algorithm is called as backpropagation algorithm. We define an error function, then we try to minimize this function where these partial derivatives and gradients are used. So this is how the minimization of convex minimization is called as. So how this is called as gradient descent algorithm. So this is how the net weights are modified and updated with the help of. We start with random weights. So there could be a question: how does it learn the weights? So what I do is I get start with random weights. Definitely, I will not be able to correctly classify. I'll get a wrong answer. I'll find out what is the error I got, and then proportionally I will go back. That's why it's called as back propagation. I will go back and proportional to the error, I will change my weights and bias. So that idea should be very simple. It's a very simple idea of you get an error because you do not know the weights to start with random weights. You got an error. This error is back propagated so that you update the weights by calculating some gradients and derivatives. We call it as gradients because it is a multivariable problem. If it is a single variable problem, we call them as derivatives. If it is a multivariable problem, because multiple weights are there, multiple connections are there, we call it as a gradient. So we calculate all these partial derivatives of how much each weight should be changed, how much bias should be changed. So this is the level of mathematics that are involved. So you should really enjoy the kind of mathematics in understanding the back propagation algorithm. So this is how it happens. So you see that finally these are the equations which will be able to operate those. You will calculate H, you will calculate O, and then you will update your W2 as W2 plus sum n. B2 is updated as B2 plus sum n. And W1 is updated as W1 plus 7. V1 is updated as V1 plus 7. So these are the four equations which we make use of these two values, which come from the erroneous values what you got. You did not get the correct values, you got the erroneous. So these erroneous values will give the error values. These error values will give the how the weights have to be. So that is how finally this algorithm converges and gives you the correct weights and biases. What I have shown you in the calculation. In the slide I have shown you what are the correct weights for classification. So they were arrived by using this equation. Okay, thank you. Thanks a lot. I wish I have taught you the back propagation algorithm also. So thanks for your comment. Yes, sir, please. Yes, sure, sir. Sure. I will share with you the coordinators and the organizers of this workshop. We'll share the details of all the speakers. Don't worry about that. And the material also we'll share with you. Thank you, one and all. Yeah, please. Yeah, thank you, Dr. Namara. Thank you.
Good evening to all. On behalf of the Department of Mathematics and Science, I would like to express my heartfelt thanks to our current resource person, Dr. Nagal Sudhakar Garu, who gave such a good and informative presentation on machine learning models. His collaboration with the Mathematics Department for the past 25 years is significant. Despite his busy schedule in the college, he gladly accepted our invitation and gave a talk in today's session. Thank you very much to all of you. So feedback link is shared in the question and answer section and YouTube live channels. It will be live for half an hour and then we will disable it. Thank you. Can we review the session? Dear participants, you can leave the session. Session is over. Up to date. Hello? Share this one. Yes. దీంట్లో తెలుగులో చాట్ బాక్స్ Q&A సార్
Q&A, question and answer లో రావట్లేదు సార్.
అది ఊపినాడు స్లో వస్తుంది, అది రావట్లేదు అంత ఫీడ్బ్యాక్.
చాట్ బాక్స్ రావట్లేదు.
చాట్ బాక్స్ రావట్లేదు సార్, ఓన్లీ క్వశ్చన్ అండ్ ఆన్సర్ వస్తుంది. టీమ్స్ తోనే తీసేసారు.
లోడ్ అవుతుంది.
అది ఒకటి
నేను అసలు చాలా ఆప్షన్స్ చెక్ చేశాను సార్ ఈ మధ్యలో. అంటే టీమ్స్ సెట్టింగ్స్ ఉన్నాయి కదా సార్, ఆర్గనైజేషన్ సెట్టింగ్స్ కూడా చాలా చెక్ చేశాను సార్. మన వైపు నుంచి సెట్టింగ్స్ అన్ని ప్రాపర్ గా ఉన్నాయి.
లింక్ ప్రాబ్లం కాదు, వాట్సాప్ గ్రూప్ లోనే షేర్ చేస్తే
చేశారు సార్, సార్ ఆల్రెడీ షేర్ చేసేసారు. వాట్సాప్ గ్రూప్ లో కూడా ఉంది సార్.
ఓకే సార్, థ్యాంక్ యూ. ఏమొద్దు. మట్టి ఉందా?
అవును సార్.
ఓకే, నేను వెళ్తున్నాను. ఓకే, ఓకే.